Hello and welcome to another read-along in geometry. Today we are looking at section 2.3, angle measures in polygons and tessellations. This is going to be a very artsy section. So to begin with, our applied problem has a decorative floor tiling pattern as shown. It uses two types of polygons to cover the floor without gaps or overlaps. That would make for a pretty terrible walking experience, I think you can imagine. Explain why this arrangement of tiles is possible. Okay? So they want to know geometrically, how come you can do this? What is so special about these shapes that they are able to come together and allow you to have no gaps or overlaps? That's the question. And a little hint there, the answer is in the title. But we'll get to that in a moment. So what is a tessellation? Well, first, we need to know what they are made of. A polygonal region is a polygon together with the portion of the plane that is enclosed by the polygon. See figure 236, figure 236. They look exactly the same. Well, here's the secret. A polygon is technically only the outline of the shape, whereas the polygonal region is the outline plus all the stuff in the middle, right? It is solid. And so anytime you play with little plastic polygon shapes, they are actually polygon regions. If you bend, say, a shape out of wire, now you've truly made technically just the polygon. And it's a minor technicality, and we're not really going to worry too much about it, except in this section, please note we'll be dealing with the regions themselves. Okay? We can arrange polygonal regions to cover a plane just as we can arrange ceramic tiles or carpet squares to cover a countertop or a floor. Such an arrangement is called a tessellation or a tiling if 1. We can cover the entire plane without gaps. Okay? And 2, no two polygons overlap. That is, polygons share only common sides. Figure 237 shows some partial tessellations of the plane. Notice, technically we will always have partial tessellations. The plane, a true plane, is infinite. So we have to assume you had infinite tiles. Could you lay the tiles down without any bumps, going over top of each other or leaving any gaps in between? So that's a good definition to have, right? Share common sides. Okay. So take a look at these guys here. We have some simple squares. Here's some triangles repeating. And you can imagine if I was to, copy and paste this, I could add on to it forever and ever. This one, well, I don't know if I would copy exactly, but you could theoretically keep going in this style, right? There's no gaps. These are all shapes, right? I haven't gone and put in something like that. Oh, there's a gap there. It doesn't quite line up. Okay, that's what we're trying to avoid. So where does this come from? Well, it all comes down to the angle measures in a triangle. We may use a tessellation composed of triangles to develop a useful relationship among the angle measures of a triangle. Figure 238a shows a triangle that we can use to tessellate the plane. So this one triangle gets repeated to create the whole tessellation here. That is, we can arrange identical copies of the triangle to cover the plane. That's what I just said. And you can see that there in figure B. Notice that the sum of the angle measures in each of the triangles is a plus b plus c. Okay? We've labeled angles A, B, and C inside the triangle, and so if I wanted to add all of those up, I would add A plus B plus C. However, because of the arrangement of triangles, we can see that the angles labeled C, B, and A in 238C, right here, form a straight angle. Look at that, straight angle right there, okay? Hence, C plus B plus A must equal 180 degrees, definition of straight angle. However, C, B, and A are the angle measures in any one of the triangles. Okay. Thus, the sum of the angle measures in each of the triangles is 180 degrees. This relationship holds true for any triangle, and we state it in the next theorem. We will prove this theorem formally in Chapter 5. But just to give you an idea here, notice we never specified anything specific about this triangle. We didn't set it at a particular angle or a particular size or anything. And so that allows us to say, well, since it's the general triangle, this will hold true for generally any triangle. Okay. So there it is. Theorem 2.1. So remember, a theorem is something that we, yes, believe to be entirely true and accurate and can be proven based on prior definitions and postulates. The sum of the measures of the angles in a triangle is 180 degrees. A nice picture there. Right, and then we can use this theorem to find missing angle measures in many geometric figures, because a lot of things include triangles or can be broken down into triangles. Take a look at this example. Find the missing angle measures in figure 2.39. Congruent angles and right angles are indicated. Okay? So here is triangle A. We've got one angle here, one angle there. We don't know the measure of this angle. So let's let x equal the missing angle measure in 240A. They've reproduced figure here now with the included x. We know, based on that theorem, x plus the 65 plus the 34 must all equal 180 degrees. Therefore, x plus, combine like terms, 99 equals 180, or x equals 81. They just subtract 99 from both sides. Simple algebra solve one-step equation, right? How about B? Back to this guy. What are we looking for? Well, we know this angle is a right angle, and look at this triangle here. Kind of overlaps with this triangle there. Or we can look at this as three triangles meeting, and we've got these angles here. Lots of stuff. So what they've done is they've fully numbered and labeled everything so that we can refer to things, right? This is why things have names. So instead of having to say that angle over there, oh, angle 1, angle 2, angle 3, 4, right? Triangle PST, or whatever you want to, right? PQR, right? So first we're going to number the angles with missing measures and label the vertices. Consider triangle PRT, so this one down here. Because the sum of the angle measures is 180 degrees, and angle 5 equals angle 6, because they have the same, arc marking congruent angles, we can say angle 5 plus angle 6 plus 124, the given, equals 180. Subtract 124 from both sides, so 5 and 6 must equal 56 degrees. Since they're the same, that's the same as saying twice angle 6 is 56. So angle 6 must equal 28 degrees, which means angle 5 also measures angle 28 degrees. We might notice that angle QRT, is a straight angle. Therefore, angle 2 plus 124 degrees equals 180 degrees. So angle 2 equals 56. Likewise, angle 3 equals 56, right? Another straight angle along there. Now we know the measures of 2 of the 3 angles in triangle PQR. So PQR, now we know that's 56 and that's 90. We can find angle 1, right? 1 plus 2 plus the 90 degrees is going to give us 180. Substitute in our known value for 2. Combine, subtract. Angle 1 must be 34 degrees. In a similar way, we can use triangle RST to find the measure of angle 4 to be 71 degrees, because we now found this one, we know that one, subtract to find angle 4. Because we know the measures of 2 angles in the triangle are 53 degrees and 56. Therefore, we have found the following. Angle 1 equals 34 degrees, angle 2 equals 56 degrees, angle 3 equals 56 degrees, angle 4 equals 71 degrees, angle 5 equals 28 degrees, and angle 6 equals 28 degrees. Okay, what more can we do with that information? Remember I said everything is made of triangles. So now let's look at the vertex angles in a polygon, beyond just triangles. The angles in a polygon are called its vertex angles. Okay. For example, in figure 241a, the vertex angles of the pentagon, right here, are angle V, angle W, angle X, angle Y, and angle Z, because the vertex of the angle is a vertex of the polygon. Line segments joining non-adjacent vertices in a polygon are called diagonals. Okay. And I bet you could have spotted the diagonals on your own. If I asked you to draw them, you could probably come up with it's something we see all the time, but this is the formal definition. They are segments joining non-adjacent vertices. In figure 241b, we have segment WZ and segment WY are two of the diagonals of VWXYZ. We can find the sum of the measures of the vertex angles of a polygon by subdividing the polygon into triangles using diagonals. Wow, there's a lot going on there. We're going to find the sum of the measures of the vertex angles. Okay? Remember, that's what we did with the triangle. We said it was 180. How do we do that? Subdividing the polygon into triangles using diagonals. Okay. So how about this guy? For a pentagon, how do we do it? Find the sum of the measures of the vertex angles of a pentagon. What do? Draw a pentagon and then divide it into triangles by drawing in all the diagonals from any one vertex, okay? Like they did in 241b. From one vertex. You could, of course, draw many more diagonals, but we're just going to focus. One vertex, all the diagonals. So that will divide it perfectly into exactly, in this case, 3 triangles. And the sum of the angle measures in a triangle is 180 degrees. In 241b, we have A plus H plus I equals 180 degrees. A plus H plus I, so this guy here. And B plus G plus F equals 180 degrees. And C plus D plus E equals 180 degrees. Thus, the sum of the vertex angles in pentagon VWXYZ is 3 times 180 degrees equals 540 degrees. Okay? And this works because every angle of the triangle is a part of one of the vertex angles, or even the whole, right? Vertex angles of the polygon. If I was to add in any other diagonals, not only would I have non-triangles in here, but any triangle I do have, its angle would not be part of the vertex angles of the polygon. We can generalize the technique used in example 2.5 to find the sum of the measures of the vertex angles in any polygon. In the pentagon, 3 triangles were formed by drawing diagonals from one vertex. In a polygon with n sides, n minus 2 triangles will be formed. This leads to our next theorem. 2.2, angle measures in a polygon. The sum of the measures of the vertex angles in a polygon with n sides is n minus 2 times 180 degrees. Put that in your notebook, right? Is this a formula worth memorizing? I think so, but it's also not necessary, because if you can understand and remember the concept of dividing into triangles, you can very quickly say, oh yeah, how many triangles can I make out of this? 3. Oh, it's just 3 times 180, right? So you don't really need to memorize it as a formula if you memorize it as a process, whichever is easier for you. Okay, so let's look at now some regular polygons. What are regular polygons? They have more fiber in their diet. Regular polygons are polygons in which all of the sides are congruent and all of the angles are congruent. So squares and equilateral triangles are examples of regular polygons. 3 other regular polygons are shown in 242. Here they are, the regular pentagon. So they have marked all 5 sides the same, all 5 angles the same, regular hexagon, regular octagon. For some reason we always skip on the heptagon or heptagon. So sad. All right. So now can you find the measures of the vertex angle of a regular pentagon? Oh, a vertex angle. Oh, just one now, not the sum of them all. Well, we know the sum of the angle measures in a regular pentagon is 540 degrees, as we already found out in the prior example. Because the vertex angles in a regular polygon are congruent, there are 5 such angles. The measure of each vertex angle must be 540 degrees divided by 5. Right? They're all the same, which is 108 degrees. We can generalize the technique illustrated in examples 2.5 and 2.6 to any regular n-gon. Any regular n-gon. The next theorem summarizes this more general result. It will be verified in the next problem set. So here we have it, vertex angle measures in a regular polygon. So if you want the single vertex angle of any n-sided regular polygon, do note, must be regular. It is n minus 2 times 180 degrees, all divided by n. We've just combined those 2 steps into one now. So, using Theorem 2.3, we can calculate the measure of a vertex angle in any regular polygon. Table 2.1 contains a list of several regular n-gons together with the measures of their vertex angles. So the most commonly used polygons. Here is the result already put together for you. So 3 sides, regular 3-sided polygon, the equilateral equiangular triangle, 60. For 4 sides, 90. 5 sides, 108. 6 sides, 120. 8 sides, 135. And for 10 sides, 144 degrees. Worth at least, if not memorizing directly, at least building familiarity with this list of numbers, so when they show up you will not be surprised and you can quickly spot and like, oh, 135, ooh, I know that's one of the special ones somewhere, and work out which one it's supposed to be. Notice that as the number of sides in the regular polygon increases, the measure of one of the polygon's vertex angles also increases. Right? This is increasing. These are all increasing. We can use Theorem 2.3 to determine the number of sides in a regular polygon if we know the measure of a vertex angle. Next example demonstrates this. All right, good old working backwards. So, example 2.7, a vertex angle of a regular polygon measures 157.5 degrees. How many sides does the polygon have? Well, just quick reference, mental check since it's right here. 157 is more than 144, so we would expect more than 10. Can you agree on that? Let's find out. We know that the measure of the vertex angle will be n minus 2 times 180 divided by n, where n is the number of sides of the polygon. In this case, n minus 2 times 180 degrees divided by n equals 157.5 degrees. We can find n by solving this equation. It's fairly straightforward. Okay, it might not be as simple of algebra as the other ones, but it's all very doable, right? First, multiply both sides by n, so we get it out of the denominator. Now go ahead and distribute that. So we get 180 times n minus 360, right? 2 times 180 equals 157.5 n. And then we're going to subtract 180n from both sides, so we get rid of it here, and now it's negative 22.5n left, but negative 360 on this side, so divide both sides by negative 22.5, right? Not so bad. So n now is 16. Therefore, the polygon has 16 sides. Okay? And now back to the tessellations. A regular tessellation, back to blue, is a tessellation composed of regular polygons that are all the same size and shape. Okay? That is to say, not only are all of the shapes in the tessellation regular polygons, but they're all the same regular polygon. I believe if you used multiple different but still regular polygons, for example, if you combine some triangles and hexagons, I think that would be called a semi-regular tessellation. So here are 3 possible regular tessellations. Here's all squares, triangles, and hexagons. To form a regular tessellation, the polygonal regions must fit together exactly around each vertex. All right? So here we go. Here it is. Why do tessellations work? In other words, the sum of the vertex angle measures must equal 360 degrees. Highlight that. That is important. The sum of the vertex angle measures must equal 360 degrees. For example, in the case of the tessellation of squares in 243A, right here, 4 90-degree angles fit together around vertex P. Work for any of them. We're going to pick this point just for reference and add up to 360. Right? Go ahead and look at that. Right? We've got this 90 degree here, this 90 here, this 90 here, this 90 here. So all the way around this point, 360 degrees. This tessellation is possible because 4 times 90 degrees equals 360 degrees. That is, 90 degrees is a factor of 360 degrees. If the number of degrees in the vertex angle of a regular polygon is a factor of 360, then a regular tessellation can be formed using that regular polygon. Look at that again. If the number of degrees in the vertex angle is a factor of 360, then a regular tessellation can be formed. Using table 2.1, we can see table 2.1, that was this list of vertex angles here. We can see that 60, 90, and 120 are measures of vertex angles of regular polygons that are also factors of 360. Also, when n is greater than 6, the vertex angle measures is between 120 and 180, right? Anything more than 6 sides, right, must be more than 120. Hence, it will not divide evenly into 360 degrees. Thus, the only possible regular tessellations are composed of equilateral triangles, squares, and regular hexagons, which are the regular tessellations in 243. Right? They tricked us. They said, oh, here's 3 possible regular tessellations. Then we find out, wait a minute, those are the only 3 possible regular tessellations. Again, to use the exact same regular polygon through the whole thing. So, back to our original tiling problem. Why did that tessellation work? The tessellation pictured is composed of squares and regular octagons. If that wasn't immediately obvious, let me outline them for you. We have squares here, and 1, 2, 3, 4, 5, 6, 7, 8, an octagon there. Each vertex angle of a square measures 90 degrees, and each vertex angle of a regular octagon measures 135 degrees. When 2 octagons and 1 square are placed together at a common vertex, the sum of the measures of their vertex angles is 2 times 135 plus 90 equals 360 degrees. So we've got that, and then the other, oh, come on, let me drop, there we go. The octagon there, so they are all centered around this vertex here. 2 octagons and 1 square per vertex. Thus, the region surrounding the common vertex is completely covered without any overlap. This tiling, composed of regular polygons of different types, is an example of what is called a semi-regular tessellation. Oh, hey, I was right. I said that before. Tiling composed of regular you know what? Actually, highlight that. Tiling composed of regular polygons of different types is a semi-regular tessellation. Okay. And finally, geometry around us. This is one of my absolute favorite shapes ever created. In 1985, chemists at Rice University discovered a new form of carbon with some unique geometric properties. Carbon-60, right? That is to say, a molecule composed of 60 carbon atoms, also known as Buckminster fullerene, or Buckyball for short, because its shape is similar to the geodesic domes of Mr. Buckminster Fuller. So he was an architect who made cool buildings that looked like this. Then they found a molecule that looks like that, named it after him. Buckyball molecules are composed of regular pentagons and hexagons and resemble soccer balls or symmetrical spheres. Okay? It's a little hard to see on this picture because they also include all the ones in the back, but I could highlight a few of them for you. See, there's a hexagon, and here is a pentagon. If I was to color those alternatingly, some white and some black, you would have the classic soccer ball shape. Okay? Their unique properties prompted physicists and chemists to envision many exciting potential applications, including lubricants, drugs, fuels, batteries, and high-strength materials. As yet, no such products have been developed. The research continues. Although we are getting really close, they have taken a string of buckyballs and actually kind of torn apart their ends and connected them together into carbon nanotubes. And so instead of a single sphere, it's a cylinder, right? Still using this alternating hexagons and pentagons connecting. And you get a much longer tube, and you can create a thread of that, and that's the carbon nanotube, carbon nanofiber. And we're really close. The issue now is the making manufacturing affordable. But we're on the verge. We're on the verge. It's almost there, okay? And then soon we'll be wearing, super high-tech, awesome, indestructible clothing made out of geometry. It's going to be awesome, okay? Anyways, that's going to do it for this read-along. Thank you very much for joining me so long. Farewell. Enjoy the rest of your day.